Ready.
Okay.
I'm recording.
Just silent mode your phone, Rashawn.
Yo, okay, whatever. Radical Researcher Society, thank you for coming. This is the third meeting. Some background. Oops. Okay, wait, let's go back. Okay, yeah. So, we want to learn about research and teach fun topics at a high academic level. So that's the goal of the club. We're probably going to have weekly meetings next week, and so, yeah.
Next week?
Or next year. And then I'm also thinking of hosting like some workshops over the summer. So if you're interested, then you can state your interest in the forum. That's later. And so today's presenter is Tejo. Yeah, Tejo.
Liam, what's his last name?
Madhavarapu. So yeah, he'll be talking about music genre classification.
Hello, I'm Tejo Madhavarapu. I'm a sophomore, and today I'll be presenting on music genre classification using an interpretable model. So first, we need to clarify one thing. Model doesn't always mean AI. Sure, the word model is used a lot in the AI world, but to start us off, we'll give examples of some other models. So, do you recognize something like this?
Yes.
Yeah, it's basically a line of best fit, but it is also kind of a prediction model called a linear regression. What it does is, using the time spent on the test, it tries to predict someone's test score. As you can see, it definitely goes wrong quite a lot of the times. Like this one, the prediction's like 20, but the student actually gets 10. But overall, it seems to be pretty good at predicting. So this is a kind of model called a prediction model. By model, I mean just something that uses things like this, predictors, they're called predictors, to make predictions. So this is called a regression model. And there's another kind of prediction model called a classification model. What that kind is rather than trying to predict like a numerical test score, it's just trying to classify. For example, like you see often as a beginning example for AI, just look at a digit and figure out which digit that is. There are 10 options. So that would be called a classification model, if that makes sense. So another example that's non-AI is something like this. If you've got two predictors, x1 and x2, and you've got like a bunch of points, you want to classify them as red or blue, then like if these points are blue, the points that are marked blue are blue, and these points are red, you can see that there's roughly a dividing line here, where most of the points above it are red, and most of the points below it are blue. So like this line, it's basically a model. Like it tells you that everything to the top left of it is red, and everything to the bottom right of it is blue. So you can like use that line to drive a model. Rashawn?
What do the dot colors represent?
The dot colors?
Yeah.
Oh yeah, basically the two classes of points. Like red and blue could mean boy or girl, it could mean cat or dog, it could mean Republican or Democrat, it could mean like any possible classification.
So the dot colors are the like real life test case and
The dot colors, what they are is like what you're trying to predict, what you're trying to guess based on these two, x1 and x2. Does that make sense?
yeah.
Okay. So now that we understand what a model is, we can move on to talking about the problem within music genre classification. And this is a problem that has been investigated before. And in 2002, some researchers achieved like a 60% accuracy using a bunch of standard statistical models. By standard, I mean non-AI. Liam?
What is music genre classification?
Okay, basically if you have like different songs, like trying to figure out like which genre each song is in. So in comparison to this, like humans, they generally get 70% right, like on that data set. But the issue with these methods that were used in the previous paper is that they don't illustrate the characteristics that define a genre. So like what in particular makes pop different from rock, or like pop different from jazz? And so our question is, what are these defining characteristics? And how effective will they be in like classifying genres, telling them apart from each other? And so this is quite useful if you're trying to like write a song for a specific genre. Yeah, I think I'll wait for that.
Hybrids, we got a yearbook distribution, and we're selling all that. to reply, Bert?
Okay, don't go to that until the presentation's done. So the use cases of this is like, if you're trying to make music for a specific genre, you wouldn't want just like a general purpose classifier. You'd want something that tells you like what kind of music will be, like what are the qualities of music in this genre? What are the qualities of music in that genre? So in particular, if you're trying to manufacture an instrument to suit a specific genre or buy an instrument for a specific genre, this is something you'd be interested in. Like for example, acoustic pop, the kind of music I write, it like needs kind of a brighter sounding guitar. Which is why I got this, which is a pretty bright sounding guitar. So now that we understand what the problem is, we can talk about what data we'll be using to solve the problem. The data that we'll be using is called the Jeet-Zan dataset. It's from, I think, 2002. And it consists of music of 10 genres: blues, classical, country, disco, hip hop, jazz, metal, pop, reggae, and rock. So each data point is basically a 30-second file of music, 100 files per genre, so there are 1,000 data points in total. And of course, with each data point, you've got its associated genre. You've also got like 58 numbers that kind of describe some of the qualities of the sound. So they're all predictors. Like thinking back to what predictors means from a few slides ago, basically it's like the kind of information a model could use to predict the genre. Does that make sense, everyone?
Yeah.
Okay. Avi?
So like for the numerical predictors, like what are examples of what they could be? Like how could you represent those in numbers?
Yeah, I'll get to that later.
Okay.
Rashawn?
I was curious, how does the model like parse these music files to be usable by like whatever you're training it with?
Oh yeah, the model doesn't do it. It's like just some program that like kind of looks at the sound waveform or whatever and extracts the numbers. I have no idea how that actually does that because it was all done by the previous researchers who made this awesome data set. And you?
I had the same question as the
Okay. So this is an illustration of what like a visual representation of one of the data files would look like. It's called a spectrogram. Basically what a spectrogram is it's kind of a plot of like which frequencies are common at which time points. Like for example, so the x-axis is time, the y-axis is frequency, and kind of the brightness is like how loud is that particular music frequency at that time. So like you can have like a really high note at this point in time, which would be like somewhere up here, or a low note at this point in time, which would be somewhere down here. As you can see at this point of time, there are a lot of low notes. Does that make sense, Liam?
Mathematically, how are frequencies represented?
Like how the frequencies decided, or
Like how's it represented mathematically as a wave?
To be honest, I don't know the full details. I think it uses something weird called a Fourier transform, but I don't really know about it. So now our methodology would be like, as we mentioned earlier, we want to make a model that we can make sense of that illustrates the defining characteristics. So the predictors that we will use, we're not using all 58 of them. We're only using the ones that we can make sense of. Does that make sense? And so let's look at these first two, centroid and roll-off. Basically, I think the best way to illustrate that is, let's go back to the previous slide. So you see how like frequency is plotted on this y-axis in the spectrogram. So the centroid would kind of be, what is the average frequency? So it might be like here-ish. That's what the spectral centroid is. And the roll-off is like kind of what is like the close to maximum frequency. That is like maybe somewhere here that like 85% of the sound is at below this frequency. And only a tiny bit, 15%, is above this frequency. Does it make sense what centroid and roll-off are?
Do different genres actually have like distinct average roll-offs and centroids?
We'll find out in the next few slides. So we looked at centroid and roll-off. Now the third predictor that I'm interested in is called the zero crossing rate. Basically what that does is it kind of measures like noise to music ratio. Like if there's more music compared to noise, there'd be a lower zero crossing rate. And if there's more noise, like such as like a distorted guitar, that's pretty noisy, kind of. Like if the guitar is really distorted, it would have a high zero crossing rate, whereas if it isn't distorted, like the sound isn't distorted, it would have a low zero crossing rate. Rocco?
You talked about like spectrograms earlier. Is it possible for like, or has there been research done before where like researchers have taken like a picture or an image of that spectrogram and fed it into a model, and has that achieved accurate results? Like, do you know anything like that?
I don't know anything about that, but I'm assuming it will be kind of the same because like I think there are mathematical procedures to construct a waveform from a spectrogram and a spectrogram from a waveform.
Mathematically speaking, or how do you define music and noise?
Okay, good question. So the zero crossing rate, mathematically speaking, has like kind of a complicated definition. Or I mean the definition's simple, but understanding what the definition actually means is kind of complicated. So basically like, let's say you've got like just one note of a certain frequency, then the note's waveform will look something like this. Sine wave. If y'all have taken trig. So this is what the note's waveform will, like, if you're graphing like pressure over time, this is what the waveform will look like. And as you can see, it crosses zero like at regular intervals. Does this kind of make sense? So on the other hand, if it's like more noisy, you'll have something more like, as you can see, it like crosses zero a lot. Yeah, something like this. So like you get quite a few zero crossings here, and quite a few zero crossings here, and quite a few zero crossings here, and so on. So like the zero crossing rate basically measures like how many zero crossings there are.
Oh, I see. So it's sort of measuring like how many how loud the harmonics are.
Or not harmonics, but like just higher frequency kind of noises.
Okay.
So does that make sense, everyone? Now, one thing that's important to do before feeding our data into the model is to take the logarithms of the predictor values. To illustrate what that means, I've got this here. So on the piano, you see how these notes are equally spaced? This A, and this A, these three notes. But like numerically, this has a frequency of 220 hertz, this is 440 hertz, and this is 880 hertz. So 220, 440, and 880 aren't like evenly spaced. Does that make sense? But there's another thing we can see about this. This is twice this, and this is twice this. So in some sense, they are kind of evenly spaced. So that's basically what the logarithm is quantifying. Basically, what that does is rather than having something like you've got the space between 10 and 100 much bigger than the space between 1 and 10, which is also much bigger than the space between 0.1 and 1. You've got like a scale stretched out in such a way that the space between 0.1 and 1 is the same as the space between 1 and 10, is the same as the space between 10 and 100. Basically, each factor of 10 is a constant increase, kind of. Raghav?
So on a spectrogram, is it also represented on a logarithmic scale? Like, I mean, like for example, like the distance from like 2 points on the left side, like would the same distance between 2 points on the right side, would it be like, would the hertz difference like be the same or would it be different?
Oh, that's actually a good question. I don't know that much about spectrograms, but I think like, does this kind of illustrate why we want to take logarithms? We want these three notes to be evenly spaced, so that's why. Does that make sense? And so also to evaluate our model, to like see how well it does, we don't want to just feed it all the data, let it look at all the data to like figure out what the model is. So let me tell you about this idea of training and testing data real quick. Basically, if you've got like, let's go back to the linear regression idea. So if you've got like this plot and you've got a few data points, then you can like fit a line to them, something like this, to like predict the y value based on the x value. Does that make sense? So the idea of what this is doing is it's trying to like, given a different x value, like it's basically something that can help us guess, like in the future, if we get a different x value, what will the corresponding y value be? So like for example, at this x value, we'd expect a y value somewhere up there. Does that make sense? But one thing it's not doing is trying to predict for these particular data points. It's trying to predict for new data. So basically to like test our model well, we want to kind of simulate that idea. We only feed our model like part of the data, in this case 80% of the data, and then it doesn't know about the other 20%, so then we use the other 20% to test the model. Does that kind of make sense? It's kind of like how like in class you go over some questions and then some other questions appear on the test. So like kind of the stuff that you do in class is kind of training data and the test is testing data, kind of.
Why can't the percent of 80 to 20 become different? Like 70 to 30, 60 to 34, 32? Why
Yeah,
can't it be
like the reason is normally we do like in data science, normally we do 80% training, 20% testing. But yeah, we could totally do something different. Like it isn't like this is the only thing that works, it's just the standard for data science. Does that make sense? So now, our model is going to be a special type of model called QDA. Basically what it does is, like you see this, it's kind of a two-dimensional bell curve. It's called a multivariate normal distribution. And what that does is, like, it's kind of, what the QDA does is it kind of guesses that each genre's predictors are kind of a 2D bell curve. Because like normally things tend to be in bell curves, either 1D or 2D bell curves. So it guesses like, for each genre, the combination of like centroid, or log centroid, log roll off, log zero crossing rate, will kind of conform to a 2D or 3D bell curve.
Is
Avi?
that 3D or am I stupid?
Oh yeah, by 2D bell curve I mean like, yes, this is a 3D plot. You know how it's like two predictor dimensions and then one is the probability. So the z-axis is basically the probability.
So you're considering like a combination of the x and y axis and then the
Yeah,
z-axis?
yeah. So like for this particular combination that's right in the middle, that's a quite likely combination. Whereas this combination of like 3, 3, the bell curve's like barely above 0 at that point.
Okay, I see.
Does that make sense, everyone? So what this model does is it kind of like tries to fit a 2D bell curve to each possible set of points. Yeah, you can't see the blue points here, oops. But for these pink points, it would kind of guess that it's like somewhere in this direction. Like the pink points kind of conform to a 2D bell curve that looks something like these ellipses are like here-ish, and the blue points, they're like clustered here and here. So you kind of guess that they conform to a bell curve that's like this. Does that kind of make sense? Rashan?
Is there any circumstance where the model will predict a 0% confidence for a set of inputs?
0% confidence? No, and that's because the 2D bell curve, like, even in points like 3, 3, where it's like quite far from the center, there's always a positive chance. It might be a tiny chance, but it's always positive. So that means that you never end up with 0% confidence.
The different colored regions, not the points, that's the probability?
Yes, this is basically a probability scale that the model uses, and like specifically its predictions are like, if it ends up in one of the pink regions, the model predicts pink. If it ends up in one of the blue regions, the model predicts blue. James?
So how exactly does
Well, normally we split at 0.5, so like anything that's more likely to be pink than blue is guessed as pink. And anything that's more likely to be blue than pink is guessed as blue. And the way that you compute the probability is just like for example, for this point, the bell curve, the 2D bell curve, the multivariate normal distribution, is like the peak, like the point of the bell curve would just be a lot higher for like the pink bell curve compared to the blue bell curve. So like that just means pink is a lot more likely to occur at this point. Like most of the time, if you get a data point here, it would be pink. Does that kind of make sense? So then, once we do QDA, we also have like, looking back at our goals with this model, the goal is to identify like what are the defining characteristics of each genre. So we want to make sure that we don't just use all the predictors that we can. We want to like select an important subset of the predictors, if that makes sense. So the way that we do it is we just try out each possible subset of the predictors and see which one works best. But of course, when seeing which one works best, we can't use the testing data. So because the testing data is just a final test, you know, you just choose one model, you test it, see how well it did, usually. So we use like a trick called cross-validation to figure out like which of the models is the best without using subsets, when using subset selection and without using the test data. I can go into more detail on cross-validation if anyone's interested, like at the end of the presentation, because I think we're kind of running out of time. So, some results. So the chosen predictors are the logarithm of the roll-off and the logarithm of the zero crossing rate. So not the logarithm of the centroid. It turns out that's not very useful in predicting genre, but when compared to roll-off and zero crossing rate. The accuracy of our model is 35.5%. Can anyone like tell me like for a random model, how accurate would that be? A model that just randomly guesses. Raghav?
10%.
Yes, because there are 10 different genres. So as you can see, this model does a lot better than random. And not nearly as good as like the 60% model from previous researchers, or 70% like humans, but still pretty good considering that all it's using is just 2 predictors. So here are some plots. This is what our data looks like. As you can see, there's kind of a clustering of like these purple points up here. Those correspond to the pop genre. There's also these blue points up here. You see? Those correspond to metal songs. So like this is log roll-off, log ZCR. I know it isn't very clear here, but like so pop and metal songs, they tend to have like a high log roll-off, or a high roll-off basically, and a high zero crossing rate. Rashawn?
Is this kind of like input pattern? If you put in more indicators, is it susceptible to overfitting?
So like more predictors?
Yeah.
Yes, but with just 2 predictors, our model is like, I think our model uses like 40 parameters or something, which is like not susceptible to overfitting. Raghav?
Oh yeah, I was just for the log roll-off graph. Why are the pop genre or the genre different genres defined as ellipses? Is that like how the roll-off? Is that how roll-off is defined, or?
Oh no, that's not that. This isn't like the definition. Kind of. It's basically like kind of trying to show where roughly the 2D bell curves kind of are, like in which direction they're stretched and whatnot.
What is overfitting?
Oh yeah, overfitting, basically what that means is if you allow your model to like use too many predictors, and what happens then is it tends to get all the training data right, but doesn't really learn anything, so it screws up all the test data. Like for example, if you're like memorizing an answer key to prepare for a test, of course it would only help you on the homework assignment for which you memorize the answer key. So that's basically what overfitting would be. So now this spot, what it does is it kind of tells you like in which direction and like where each genre tends to be. Like, so let's look at this one. This orange ellipse, it corresponds to classical music. What this means is like it tends to have a low roll off because it's on the left. It also tends to like be stretched out in this direction. So like classical music that has a high roll off also has like a somewhat high ZCR. So like actually all the ellipses, as you can see, are stretched out somewhat in this direction. If that makes sense. So now we can see like looking at our observations from earlier about metal tending to end up in the top right, that reflects here. Same with pop, that's here. But one important thing to understand about these ellipses is that they don't like try to contain most of the data in each genre. Like for example, this orange ellipse here, that only contains like 8% of the classical songs. And this would only contain 8% of the pop songs in the data set. So it might look like they're quite separate from each other, but in reality they're not. If we try to contain like 95% of each genre, you need way bigger ellipses, like something like this. Like 6 times the radius of each of these. Does that make sense?
For a predictor like roll off, where that's like about the frequencies, like the upper frequencies of a song, doesn't the production of a song affect that a lot? Like a certain producer of that for like the same genre could choose to cut off higher frequencies in the same song, regardless of like what genre the actual song is. So isn't that like couldn't it be more production tendencies rather than the actual genres of the song?
Yes, that's actually very much true, but our models just kind of have to deal with it. Like, if we had more predictors, we might be able to tell more, but the idea of the models that we chose is like only these predictors, and that's also useful in telling like the producer like for a specific genre, like how should they try to produce the song. That's like another like reason. So like for pop, they should like try to leave in the higher frequencies, as you can see, like log roll off. Whereas in like maybe jazz, I think they shouldn't have as many higher frequencies, and so on. That's kind of the idea of how this can be used. So do these two plots make sense? So now this is something that tells us like kind of how well our model did. Where it screwed up, it's called a confusion matrix. To understand this, let's look at the pop column. This corresponds to the 20 pop songs in the testing data set. So as you might remember, like testing is 20% of the full data set, which has 100 of each genre. So this column is the 20 pop songs in the testing data set. So like the 14 here means that it got 14 of them correct. It predicted pop for 14 of them. It predicted disco for 3 of them. It predicted hip hop for 2 of them. And it predicted rock for 1 of them. So as you can see, for pop in particular, the model tends to do quite well. But it also is like not very good at predicting hip hop or rock. And the reason for that is hip hop and rock, they both tend to end up like right in the middle of the data. Like rock is this ellipse over here and hip hop is this ellipse. So like quite frequently, like as I said, like to contain most of the rock songs, you want an ellipse this big. So like you might end up with like a rock song over here, and then the model will guess that's pop. You might end up with a rock song over here, and the model would guess that's jazz. Only like in this, like kind of close to this ellipse region, the model will guess that it's rock. So that's kind of why the model isn't very good at predicting rock or hip hop. Anyways, thanks for listening. Any questions, everyone?
That was a nice presentation.
Rock, give me my
So, yeah. Please fill out feedback form. And then, like, yeah, I'm gonna try to host some workshops or something over summer. Because basically to help you learn how to read research papers and present on them if you're interested in being a presenter next year. So, yeah.
Cool.
Yeah, thank you.